This is a talk on general industry people. And so I think it might be interesting for you to know how I actually got to where I am. So I'm originally from Michigan. I went to Michigan Technological University, got an electrical engineering degree there at a bachelor's. And I started out of work at a startup doing circuit design, so like PCB circuit design. I found it, I mean, it was boring, it's fine, whatever. But I had an email sent to me over the summer asking if I wanted to do a PhD. This is just a general email sent out to all the alumni, and I responded to it. This PhD was funded by the Navy, which once I was finished with my PhD, they gave me a job offer to work for the Navy. I wasn't required. There's a thing called a Smart Scholar, where however many years they fund you, that's how many years you have to work back. That's not the case for this, though. I mean, they gave me a free job offer, so I might as well take it. And I'm enjoying it all the time. It's a lot of fun. The people in the Navy are very humble. There's a lot of smart people, and they're very shy about this fact. Whereas in academia, it was the complete opposite, where everyone was very arrogant and talked about how smart they were all the time. And I guess I forgot to say that I work in Rhode Island, so I live in Rhode Island right now. There you go. There's me right now. So let's actually talk about the actual science of neural networks. I wanted to start off explaining the different parts of machine learning. So to me, machine learning is actually a really broad topic. It's a general iterative nonlinear process. But the main talk nowadays is in neural networks. So I'm just going to be focusing on neural networks entirely. And to me, I think of a scale of people who are into, maybe this is like, it should have been like an iceberg thing, where I feel like when people talk about how they're dealing with machine learning, to me at the highest level, with no math at all, it's like this prompt engineering thing that I hear. I don't know anything about that because I don't do that personally. And if you're going a little bit deeper, it's something called like you're just copying someone else's models and running it in your embedded system or in your app, something like that. There's a little bit math involved, but not particularly much. To me, designing the models, that's what I did for my PhD. So obviously, since it's my PhD, it's obviously the most important thing. But then below that is like the machine learning theory and the mathematics behind it. But since this is what I actually know, I pointed at it to my screen as if you would see that. But designing models, that's what I do, and that's what I would say I have the most expertise in compared to anything else. I wouldn't call myself an expert, but I guess maybe I am. I don't know. So I want to talk about just a general broad understanding of neural networks. So in neural networks, what you do is you have input data and output data. And there's some pathway to get from the input data to the output data, but you don't particularly care. So what is the input data versus the output data? So in this case, let's just give an example right here. I have a picture of my friend's cat right here. His name is Socks. And I just want to send this picture into, quote unquote, pass it into a neural network. I'll explain what that means. And I want it to output a cat. So I'm trying to classify, does this picture have a cat or does it have something else? And what it means by passing it in is a neural network is just a series of either matrices or mathematical operations. So the general neural network is a bunch of matrices with nonlinear functions wrapped around it. But basically when you're doing passing it in, quote unquote, is you're taking this picture right here and you're taking the pixel values and multiplying them by the matrices. So you're doing matrix multiplication, and then you keep on doing that over and over again with these random weights. So if you hear like the open models that have weights in them, that's what they mean, is that these matrices have weights in them, and that is what is being learned with the neural networks. And so when you're multiplying these pictures into the matrices, that's what it means when you are passing this data into a neural network. And then when you're outputting it into a cat, there's like called embeddings, which is basically just if it happens to be a 1, say it's a cat. If it happens to be a 2, say it's a dog, or something like that. There's nothing too fancy about embeddings. It's just a way to represent information, rather a way to represent information for a computer to understand. In this case, it'd be a neural network or a machine learning algorithm. And now, when I do these presentations in the past, I really scatter in a bunch of real world examples for all of these different parts, because when I was doing these presentations before, it was mainly for trying to hype up machine learning, because people didn't care about it before. It wasn't that big of a deal. And so I wanted to show that, hey, these are real world examples of, say, this website right here. You upload a picture of a plant and it gives you what the plant is afterwards. It's like an encyclopedia of a plant, and it's actually pretty sick. I picked this one just because it happens to be that this shows that it uses a neural network. There's other plant identification apps out there, but this is the only one I found that actually said that it was using machine learning. The other ones probably do, but they don't actually represent it or actually tell you that they do that. So for me, for a neural network, what I say is that a neural network, people always say that's a black box, that you don't know what's happening inside there. There's no explainability towards it. If you're a bit technical, the term is explainability. So if you look for terms that are explainable AI, it's trying to figure out how in the world does a neural network know that this picture equals a cat? How do they know that? I mean, there's, how does this neural network operate on this input data to predict the output? And basically, there are two thought processes here. As long as it works, I don't care. Who cares? That's what this general chat GPT stuff is, where I don't really care if it works, or I don't really care how it works, because 99% of the time it works very great. But what happens with this thought process is once it's passed into new data, the neural network starts what's called, I forget what they call it. It's like hallucinating. I think ChatGPT is called hallucinating. Before that, it was called extrapolation, or I mean, that's what I called it. It's extrapolation. It's passing in data that it's never seen before, and so it doesn't know what to do. And if you don't have a good understanding of what this neural network is doing, what happens is once you pass in new data, it's going to go wild, because you have such a highly nonlinear neural network, and you don't know what it does. And if it's passed in with new data, it's in a nonlinear region where it's going to be going wild, and you haven't constrained your neural network to be in there. So it kind of freaks out, and it just starts spewing information out. And so that's kind of, to me, this is what I like about neural networks. And something that I want to show is I don't know if this is a real issue anymore, because it's been a few years since I've done these talks. But when I did these talks before, there was a lot of people who didn't know where to start in machine learning or where to continue afterwards. So to me, what I find was the nicest ones is this. There's this 3 Blue, 1 Brown YouTube series of neural networks, and it's highly visual, shows what's going on, looks at this handwriting data set, MNIST data set, and shows you how this neural network is actually propagating this data through. And so I recommend, if you're trying to understand what a neural network actually does, this right here is a really good playlist. Another one is the Stanford lectures. This is like the default original one. This is from quite a while ago. I think it's like from 7 years ago. by Andrew, and it's just the general professor who really spearheaded a lot of this modern machine learning kick. And then finally, this last bullet point is, well, if you really want to get into the nitty gritty, neural networks and deeplearning.com steps you through how to physically write code to actually make a neural network. So it steps through every single point of how this works and make sure that you can physically write everything itself without using without using a library or something like that. So these are the three things I recommend to look at. And say for someone else, say you know this already. Say you know the general theory of machine learning. Let's go on. Let's move on. Where do you go from there? I recommend there's another lecture from the University of Waterloo, and this guy shows a lot more advanced neural network architectures. So Andrew's lectures from Stanford basically goes into just a general theory of machine learning or neural networks and how the neural networks function, while this lecture right here from the University of Waterloo really steps through each architecture, how they work, and stepping through the really nitty gritty of it all. So after that, now let's start looking at YouTube videos that are stepping through more YouTube videos of each of the different neural network architectures. Because at this point, you're really just trying to find a toolkit of which neural network architectures would be best for your data that you have. So if you're at work and a boss tells you that, hey, I have this time series data and I want to pass it through a neural network, which would you want to use, say, a fully connected neural network, or would you want to use a convolutional neural network? What would you want to do? And so just having this in your repertoire of different architectures, knowing how they all work is really good to have. So say you know these different architectures and moving on, and you don't have a job yet, or you're just a student and you just really want to get into machine learning. What I recommend is after you understand the toolkits and how the different architectures work, this is when you just start reading academic papers. And I know it's scary. Reading academic papers is really scary. You're probably not going to understand the first 10 of them that you read because there's just so much terminology and so much technical jargon. You're not going to follow anything. But after you probably read it maybe 10, 20 times, and maybe you start to glean some information off of it. But once you start understanding once you can get past, say, the jargon, you can be blazing through these papers and just start writing it up in Python. Try to verify the results, which is called a replication study. That's the technical term. Just take their paper and try to reproduce everything that they're doing. Just step it through and go through and create the neural network, follow what they're doing, just blindly follow it and try to get your neural network to produce the same results that they have. And that will really let you know the entire process of how to take your input data, say this data set that you have, and really learn how the pre-processing, how the neural network works, how the training of it works, and the general flow of everything about data science with machine learning. And then the last little bit is Kaggle.com is a website that has a bunch of different challenges where they're showing a bunch of different data sets, and they don't care what you're using. They just want to get the best results, best accuracy of each data set. So these are the 3 steps that I recommend you look at if you're trying to get into machine learning. And so that's that right there. And now say I put this in here because this information is really hard to find. Advanced neural network techniques and tips, tips and tricks. I don't know if this is very applicable to the audience in this talk, but maybe if in the future you want to look back at this and think about different ideas of what should be done in a neural network. And so I'm going to step through the 3 different steps of a neural network. There's your training data. You're curious about your training data, and you want to look at, after that, you want to look at your loss function. What are you trying to derive with this data? What are you trying to like get out of it? And then backpropagation and kind of the general model architecture. And as an aside, there are parallels to statistics. And in fact, to me, it was statistics a while ago. And so this training data before machine learning, it was called a priori data. A loss function, it's quite parallel to the residual. Backpropagation is actually using gradient descent, and that's basically the Newton's method. There's a few, there's a few things that are a little off, but it's all generally the same. And so I like pushing that statistics and machine learning, they're basically the same thing. And AI, it's all the same. It's just, I mean, it's non-linear statistics, but it's all kind of the same thing. So stepping through one set of training data, when you're looking at your training data, you really want to understand what's happening in it. And I know it's going to be tedious, but I highly recommend just going through your entire data set and panning through it all. Just look at all of it and try to understand what's going on. Because if you understand what's going on, you know how to make your neural network understand what's happening. So for a tip of if you have low amounts of data, there's a thing called transfer learning, where you take data that's kind of similar to what your real data is, your actual data set, and then you train a neural network on this. This right here will make it so, you know, the neural network's not going to be perfect with your real data, but it's going to have a baseline. It's going to have the general kind of physics-based model, maybe. And then after you pass in the real data, that's just probably much more painful to deal with. You're going to get some better results because you already have this baseline of data that's kind of similar. And then another thing is data augmentation, where if you have a few amount of pictures, say, for example, you have just pictures and you're trying to classify pictures, to pass in a neural network, just rotate it or flip it or add some noise, rescale it different points, just kind of size it around a little different, add some noise into it. This helps generalize your neural network. So if you're finding that your neural network is overtraining too quickly, there could be 2 things about it. But one of them could be you just don't have enough data. And so you can do data augmentation to kind of really work with that. For a loss function, take into consideration what you want as an output. And I know I just read that verbatim, but it's really key. You really want to know, are you trying to estimate, say, the position of some data? Are you trying to classify what's in a picture? And you really want to take consideration of how many dimensions you have. So for the case of classification, do you really care if there's multiple classes occurring at the same time? So for a picture, for example, like a picture of a cat, do you care if do you just want a cat detector? Is there a cat or is there not a cat? If there's a picture of a cat and a dog, what do you do? Do you want to classify that there's both a cat and a dog, or do you want to just say there's a cat? And so things like this, understand what you want as your output to reduce the dimensionality of your output. If you reduce the dimensionality of your output, you will get better results because you don't have to do as much. Because you might have heard there's this curse of dimensionality and whatnot. All right. Anyway, the next thing is regularization. This is just tacking on an additional value to your loss function. So if you're having mean squared error of your loss function, it's an estimation of its neural network. If you just tack on, say, L1 norm, that is just taking your loss and plussing an additional value to it. And so in the case for if you're using like Keras or TensorFlow or PyTorch, which are Python libraries, they all have these L1 or L2 regularizers. What's happening here is it's summing up the model weights that are on those specific layers, and it's penalizing the value of those weights. Because what's been found is in neural networks, if you have high valued weights, it really overtrains, quote unquote. It produces really highly nonlinear results. And so you really want to, you know, try to tone down the values of your weights. All right, and so you can do regularizers on anything, just tack on other values. Another thing I want to show is batch size. Batch size is if you're taking in 10 pictures at a time and passing them to the neural network, that means you have a batch size of 10. This helps in speeding up the training process and helps in gradient descent, preventing it or backpropagation, preventing that from getting stuck in a local minima. But what I find is you can really debug your training data if you set the batch size to equal 1, because it steps through one single value and you can look at all of the weights, all of the gradients that are passing by. And it really helps in debugging to understand what your training data is actually doing to the neural network. Another thing is batch size is really key in fine tuning, same for regularization. Fine tuning is a really finicky art, and there's not much around it besides just try a bunch of stuff and hope that it works. You just kind of get good at it after a while. There's not much of a science to it. It's mainly an art. And the last little thing is backpropagation and generally just the model itself. And you really need to cater, I'm reading it verbatim, but you really need to cater your neural network to your training data. What that means is if you have a small amount of data, you can't use a large neural network because it's not going to train well. If you have a small amount of data, you have to use a small neural network. There's no getting around it. You're not going to get good results. You're going to overtrain instantly with a large neural network without a huge amount of data. And so that's what comes in with maybe transfer learning or augmentation to kind of squeeze out extra results and maybe get a better neural network. And then this right here, facilitate learning. Say if you have an image, your data is images, you really want to use something that's based off of like neural networks that work well with images. So if there's time and dimension correlation in the data, you'd want to use, say, like a convolutional neural network because it spans across those like localized areas. But if you don't know about it, there's things like a transformer neural network, which is what ChatGPT uses, which are attention-based, and those are basically a convolutional neural network, but no longer localized in a specific area. And the last little thing I want to say is gradient descent optimizers. When you're looking at Python packages and it tells you to use, say, SGD or Atom, there's trade-offs around them. Just look that up. Look up what they are and understand what you want as your output. Do you want the highest performance? Or if that's the case, use stochastic gradient descent. You'll have to maybe train maybe 10, 20 times to get a good result. Because it's unstable. It won't get the best results all the time, but it will eventually find a really good result. And Atom is an optimizer that it's just adjusting the gradient descent value. And it's highly stable. So if you just want a good result and call it good, just use Atom and then move on. And so those are my, general tips and tricks. And I feel like I kind of blazed through that. But to me, these presentations are kind of a reference in the future, just because it's a good thing to look back on. So
Thank you.
Yep.
If you have any questions, feel free to put them in chat or raise your hand if you want to use your voice to talk about the questions. First of all, Kribbles, can you talk a little bit about what you do for work. I know you can't say much, but what is the general stuff?
So I deal with underwater acoustic data. And so I have this data set from submarines, and I need to process it to get a good result. And it can be a variety of different things. It could be sonar. So if you send a ping out and get a response, you can use, say, a match filter to handle it, or you can use something else like a neural network. I use that as an example because I don't do that. So, and I don't know if we're actually doing that or not, because I can't really say much about it. So yes, yeah. Time series data. There we go.
First of all, Shane asks if you've ever had to work with synthetic data.
So I'm not sure what he means by that. Like like fake data, like simulated data, or what does he mean by synthetic?
Shane, do you want to weigh in there?
Yeah,
What do
sorry.
you? It's okay.
I, and I'm assuming it's if he doesn't respond, it's probably simulated data. One of the things I did is in my PhD, I had um, how do I describe this? So I have this time series data of trying to track a snowmobile driving back and forth, using that with acoustic data. And it was non-cooperative, it's what it's called. And so you can simulate that. And what I found, and there was some analysis going on in the acoustic field of taking simulated data, running an acoustic simulation, training off of that as your whatever I call it, transfer learning, and then running off of that afterwards, and then pulling in your real data after that. So I don't know if I just said a bunch of words, but the general idea is throw in simulated data first if you don't have any transfer learning, simulate it yourself, and then take your real data afterwards. So there we go.
J Squared asks, do you see neural networks overtaking other machine learning algorithms? They seem like an all-purpose tool.
So neural networks are inefficient with training data. I don't see it in a case where you have a high, not a lot of data. Or another thing is it's only in labeled, I forget what supervised. If you have labeled data, neural networks are a really good idea. If you have unlabeled data, you can't use neural networks. Well, there's study in this currently. It's called self-supervised learning, where you're finding patterns in the data. But in general, neural networks are good for labeled data or supervised learning. Unsupervised learning is, generally clusters or such like that. Also, neural networks are really overkill for certain applications. It might be better to just use, say, a fuzzy controller, which I guess it's not machine learning, that's computational intelligence, but the the boundaries between these names are pretty wishy-washy. So to me, I don't personally like using neural networks for every single little thing, just because there's so many cool things out there. But yes, neural networks are really, really highly important, and they do a lot of good results. So I just realized that was the most academic response of an answer ever. I did not say anything at all. No, I don't think neural networks are going to take over all the machine learning algorithms. They are very good, but I don't think they will.
How do you enjoy working for them? Like, do you think it's kind of a unique job? Is more what I'm going for there.
Yeah. So there's two things about that. I personally really like it. There's the downside is you don't make a lot of money. So I'm pretty sure I can make a lot more money working at, say, Google or Facebook or something like that. But I'd personally hate it. Um, um, and also, I'm guessing here, but I'm pretty sure the mentality at Facebook or Amazon, your coworkers are probably going to be sniping at you. In the federal government, everyone's all working together because it's basically impossible to get fired. So no one's ever bragging about how smart they are. Everyone's very humble. Um, and we're all kind of working together. You don't, and it's an extremely stable job. So obviously there's trade-offs. I don't make a lot of money. I don't make as much money as I could in other jobs, but it's a very relaxed job and it's very fun to actually work with these people because they're all really smart. Um, Currently, what I find with the Department of Defense is there is there's a gap in the age of people working at the Department of Defense. So um, there's a lot of old people and there's a lot of young people, and there's no one in between. So if you are wanting to learn a lot from like graybeards, I think the Department of Defense is probably the best point in there, or the best possibility there. But if you're looking for money, don't go to the Department of Defense. You or any federal government job, you will not make money there. So it's a stable job, and that's it. No,
Benzel asks, what would you recommend for depth and measurement analysis of specific objects in photos?
so this feels like a very specific question, and I don't know what you mean by that. Are you trying to find where in, say, if you have a picture of something far away? Let's go here. Here. Are you asking how far away is this cat from your observer? Um, if you want, it's called computer vision. There's I forget the name of it. I mean, it's OpenCV is the Python code, but I don't know exactly what he's asking for depth and measurement. Okay, an estimation of how big the cat is. So this doesn't need to use neural networks. Well, maybe it does, maybe it can, but typically you can use just computer vision. It's a, I forget the name of it. It's a it's a transform, homography. It's a homography transform. I haven't done this in like 5 years, so I'm losing touch on these terms. But in OpenCV, there's a homography transform, and it's basically you're trying to reconstruct in 3D space where this picture was taken. So this is a really bad picture because, there's not there's not much you can go off of, but you're basically looking at these angles right here, and you're noticing that these 3D, that these points right here are right angles. And so if you figure that out, you can figure out where you're taking this picture at, and then you can figure out where in pixel space this current position happens to be. So yes, computer vision, that is my recommendation.
Bud asks, can neural networks be used to learn to detect hidden cancers, such things humans can't see? Does that go under unsupervised learning?
So Nivek replied to that as well, saying, short answer is yes, but I don't know the current state of the art. Basically, but if, I guess I don't know the state of the art either, because it's been about 3 years since I had someone doing this, or my colleague was doing this. So maybe things have changed in 3 years, but what you do is you find pictures of people that don't have cancer and find pictures of people that do have cancer, and you know for a fact that this is the case. Uh, and then you can use that to detect afterwards. Otherwise, neural networks can't be used. I don't believe so, because you need to label it. Neural networks are used for labeled data, and if you don't have labeled data, you can't use neural networks in general. Yeah.
Jason has an interesting question here on education. What are your thoughts on needing a master's to get into entry-level DS positions? You got to tell me what DS means. I think I know. DS
Means
positions. What's that?
DS is data science.
Data science?
Yes. Well,
Sorry,
yeah.
data
Yep.
science. It's something I've seen people say fairly often on Reddit/YouTube. So, do you think people
Yep.
should need a master's? Does that make sense to you?
Um, this is the problem, is I have a PhD, so I'm a very uh I I don't have the same stance as getting a master's. Personally, I always recommend getting a master's just because, and I don't recommend getting a PhD. Um, Again, it depends what you're looking for. If you want to do research your entire life, you get a PhD. That's how to do it. If you're trying to get money, PhDs are the worst possible thing to do to try to get money. You're kind of going to be pigeonholed in research positions only. Sorry, you're going to be pigeonholed in research positions only if you get a PhD. And it's not saying that PhDs are bad. I'm just saying if you have a master's, it does open up doors. And um, I'm reading at the same time. I'm getting distracted. But I agree. I feel like it's harder without a master's, but I don't think it's impossible. I just exactly what Quick and Smart said. Uh, um, but I fully say go for if you can handle it. If you can get a master's and you can actually pass it and you can get the actual diploma of master's, go for it. I don't recommend getting a master's while you're getting a job because that you're going to be so stressed out. You're going to have a lot of you're going to be working full time and then you're going to be going to school at night as well, and it's going to be really painful. That's what I hear. So I really recommend if you're getting a if you are thinking about a master's and you can, as in you can financially support it, and you have the knowledge to do it, go for it as quick as possible and get it done with. You'll just get a bump in money straight up. One other recommendation is if you are in America and you're getting a data science master's, you should never be paying for it yourself. The Department of Defense really looks for data science people. And if your professor that you're talking to is saying that you have to pay for that, if your master's degree is not funded in data science, you need to find a different professor. There will be professors all over the place that are working with the Department of Defense, and they have funding for you. I do not recommend ever paying for a master's if you are in data science.
Okay. Um, that's interesting.
Yeah, sorry. Yeah, I'm a bit. Yeah, I was a bit. I guess aggressive on that point, but yes. I yeah. Yeah. Sorry.
No, I think it's fine. So, I'm sorry. Um, Working for the Navy, you obviously there's some pretty big differences between working in a little more regular job guy, I guess. Um, do you want to elaborate on those differences a bit more? I know you talked about kind of the differences between like the younger people and the older people there. Why do you think you don't really get like middle age and like middle experience people in the Navy? Was there a reason for that, or is it just kind of just what happened?
Um, I actually have no idea. We actually talk about this at work all the time. No one knows. People just leave, and we don't know why there's an age gap. I think what it is if people are dedicated to the Navy, are dedicated to the federal government, they will stay there forever. The federal government is a position where if you don't want to take any risks, that's the job for it. Because it's almost impossible to get fired in the federal government. There, you have to be trying. Well, I guess if you post, classified information on War Thunder forums, uh, that'll get you fired instantly. But other than that, like it's like the obnoxious things, like lying on your time cards or doing like sexual harassment at the workplace. Like that's basically all you can do is that's the only ways you can get fired. Um, so I uh, I don't know why there's an age gap.
Interesting. Why is it so hard to get fired? I guess like is it just a lot of bureaucracy, or is there a specific reason?
Um, I know. So it's going to get a little political, but the union in the federal government has a huge grip on everything. So it's really the union is really hard on it. So it's really difficult to uh, get an agreement with the union to fire someone in the federal government.
Mhm. Excalibur asks, I'm curious whether you see any international people at work, or anyone who isn't a citizen, and if you do, does that limit their growth due to clearance issues?
Um, so I do see a few people there because um, the U.S. government does what's the term? Collaborate. We collaborate with other countries. Um, but I mean, if you happen to be, say, a Chinese citizen, you're not going to be working for the Department of Defense in the Navy or in the U.S. That's just not going to happen. Um, I believe no. Okay, one thing. If you happen to be a dual citizen and you get a clearance, you have to revoke your other citizenships. You have to be solely a U.S. citizen if you have a security clearance. So, but that is if you're physically working in the U.S. Navy as a civilian. Um, but we do have collaborations with, say, Australia or the United Kingdom or things like that. Or Japan as well, I think. I don't know. But yeah. So I guess to get a single answer, does that limit their growth due to clearance issues? Yeah, I think so. Because you can't have a clearance if you're an international person. So there you
That would
go.
do it, yeah. All right, looking to wrap this up here. I guess as a final question here, what do you kind of enjoy the most about your job? Why do you like machine learning and all that? What's that kind of stuff so much? Is it why? And have you? I mean, I guess if you don't like it, why don't you like it?
um, so I am not a huge proponent of machine learning. I think it's just another tool. Um, I don't think it's the biggest thing in the world. I mean, it is right now just because it's doing a lot of stuff. It can facilitate huge. No one cared about it, and so it was cool to hype it up. And now that's really hyped up, I'm kind of like a hipster, where I'm like, yeah, machine learning is not the biggest thing in the world. Uh, I don't know, maybe or a contrarian or whatever. But I just think it's a cool. Uh, yeah. I I'm not a huge proponent for machine learning. I like it. It's beautiful. There's an art to it and it's cool. But um it's not a panacea. It's not the best. It doesn't solve everything. There's a lot of situations where you don't ever need to use machine learning for anything, and a lot of people are pushing for it, and I hate that. So, um, but yes,
Awesome. Thank you, Kribbles. That was very much appreciate you coming in here and doing a lecture like this.